Hi everybody. Today's lecture is going to take a look at what we're going to call a complex circuit. And a complex circuit is one that combines series and parallel circuits. Now, for example, in a typical room, or let's say your classroom, you'll notice that you can flip one switch and it may only turn on half the lights in the room, um, but not the other half, which means those lights in a way are connected in sort of a series type circuit. And that series circuit is then in parallel with another series circuit that connects to the other lights. And even with them in those lights themselves, they may be in parallel because one bulb could go out and won't shut down the whole system. So most houses, rooms, anything like that are really a complex circuit. And so to analyze and really understand what all the currents are, what are all the voltage drops everywhere in a complex circuit, can be a tricky process. And this is definitely one that, after this lecture, definitely want to make sure you probably go over in class too. But I sort of have a method that I think helps to break these circuits down into little parts, bit by bit, so that by the end of it, you really understand what's going on. And it's a pretty effective method once you learn how to do it, but it does take practice. So don't be surprised if you don't get it the first time. You may have to do it again and again. But once you get it down, I think it's pretty easy to do most of these circuits. Our first goal in this method is to always reduce our complex circuit down to the simple circuit. Now, we won't be able to do that in one step, like a simple series or a simple parallel circuit. We're going to have to take it little steps by step. And every time we make a small reduction, we're going to redraw our circuit until we're all the way down to the simple circuit. You'll see that kind of as it happens. Now, once we're there, we'll have REQ. We'll know the REQ of the whole circuit. So that's our primary goal, get the REQ first. And then what we're going to do is work our way back through those pictures that we created. And along the way, we'll be able to find currents and voltage drops for each drawing that we did until we're back to our original circuit and we should know everything. So the best way, of course, to understand it is to show you all the way through. Okay? So again, you may have to replay this a few times to really follow what's going on. Okay, so here's clearly a complex circuit. If you follow the currents, and that's the best way to sort of start, I1 comes out of that 120 volt source and passes through a 5 ohm resistor. Then it reaches a junction. And at that junction, I1 splits into I2 and I3, going down two different branches. Okay, now, so those are two different currents. So that means those two 8 ohm resistors must be in parallel to each other. But at this other junction, it comes back together. So now we've got I1 again. And I1 goes through the 7 ohm resistor. It then splits again into 4 and 5. Anytime you have a split, that must indicate something about parallel because they're different currents. But then it comes back together and I1 goes through the 2 ohm resistor, returning back to the battery or the voltage source. Now, since I1 goes through 5, 7, and 2, 5, 7, and 2 are actually in series with each other. But along the way, we have those parallel branches that sort of interrupt what would be a nice series circuit. So I've got to decide, what do I want to do first? Well, what I want to do is to start off with some what I call mini REQs. In other words, this would be a really nice series circuit if we could get rid of those two parallel groups. Well, let's do that. So what I'm going to do, I'm going to redraw the circuit. Now, that 5 ohm, I'm leaving alone. I'm not doing anything to it. But the 8 and the 8, I'm going to squish them together into one resistor, a sort of mini REQ. Now, let's pretend I don't know what it is right now. So I'll just leave that blank. The 7 ohm resistor, I'm leaving alone. I don't want to touch it right now. And then the 6 and the 3, I'm also going to squish together into one resistor. I don't know what it is yet. And then the 2 ohm, I'm going to leave alone. Okay? So notice I've left that 7, 5, and 2 alone. And I'm going to squish together those two other parallel groups. Now they're each their own group. So for example, if I did sort of a mini REQ up here, it's parallel. I've got to use that 1 over rule. So 1 over R would be 1 over 8 plus 1 over 8, which is 2/8, or 1/4. Which means that this is actually a 4 ohm resistor. In other words, those two 8s in parallel would be the same as having one 4 ohm resistor. Let's do the same thing down here. 1 over this little r is 1 over 6 plus 1 over 3. Okay, so that's 1 over 6 plus 2 over 6, which is 3 over 6, or 1/2. So that means that this resistor down here would be a 2 ohm if I squished that 6 and 3 in parallel. Now look what that's done for me. I now have sort of a new circuit that's clearly a series circuit. And now what I can do is I can draw my simple circuit from that series. Because whenever we have series, it's pretty easy. All we've got to do is just add up all the resistors. So 5, the 4, the 7, the 2, and the 2. And that's going to give you 20 ohms. And so there's my answer to REQ. REQ is 20 ohms. That really wasn't so bad, was it? Okay, a couple of quick reductions and I'm down there. So that's the first part of the method here. Redrawing the circuit till I've got my simple circuit. Okay? Now, I'm going to start at that simple circuit. Notice that of my 3 things I'm always dealing with, okay, in Ohm's law, V equals IR. That's my key equation, right? Well, I've got V and I've got R. So why don't I get I? Okay, well, I have 120 volts and 20 ohms. So that means that I must be 6 amps. Okay? Now, notice that 6 amps, this simple circuit came from this circuit above. So if there's 6 amps there, I'm going to bring that 6 amps back. Okay? Now, let's consider this series circuit. Well, I now know that 6 amps goes through every resistor because it's series. So in other words, I know I and I know R everywhere. So let's get the voltage drops everywhere. So let's follow the 6 amps. 6 hits a 5 ohm. Well, I times R, 6 times 5, means there's 30 volts drop there. 6 amps carries on to the 4 ohm. 6 times 4 is 24 volts. 6 amps keeps going around to the 7 ohm. That's 42 volts. 6 amps comes around to the 2 ohm. 6 times 2 is 12 volts. And then it hits another 2 ohm, and it's 12 volts. And now I'm going to pause for a second and say, well, am I right? Well, if I add 30 volts, 24 volts, 42 volts, 12 volts, and 12 volts, I get 120 volts. I've dropped all my voltage in a series circuit. I must be doing something right. Now, here's the really tricky part. This circuit is really this guy. So let's bring back things we already know. For example, we know 6 amps leaves the voltage source. Well, notice 6 amps is where I1 is. So I know that I1 must be 6 amps. This 5 ohm resistor is also this 5 ohm resistor. And we know that it drops 30 volts. We already know that. So we know that the voltage on the 5 ohm is a voltage drop of 30. Now, the 8 and the 8, that's new. We don't know anything about that yet. Let's skip it for a second. This 7 ohm is this 7 ohm. And we already know that the 7 ohm drops 42 volts. So we've got that one. This 2 ohm is this 2 ohm up here. We know it drops 12 volts. So we've got a bunch of answers so far. Okay, now, here's the part that people always make the biggest mistake. And it is difficult sometimes to understand, but you got to remember the parallel rule. This 4 ohm resistor represents these 2 8s in parallel. Now remember the parallel rule. They don't divide voltage, they share voltage. They don't divide up the voltage, they share the voltage. So, since this 4 ohm resistor drops 24 volts, each one of the 8 ohms drops 24 volts. Okay, now I know it's hard to understand and to buy that, but we'll show why it's got to be true here in a minute. So each 8 ohm drops 24 volts because they must share the voltage because they are a parallel group. Now, by that logic, this 2 ohm came from the 6 and 3 in parallel. If the 2 ohm drops 12 volts, then these each drop 12 volts. So voltage drop on the 6 ohm is 12 volts, and voltage drop on the 3 ohm is 12 volts. Now, to understand why we're right, let's look at what we also need to find, current. So up here at I2, well, we have 24 volts and 8 ohms. 24 divided by 8 gives you 3 amps. And down here, 24 divided by 8 for I3 also gives you 3 amps. Now let's look at why that makes sense. Remember how we started with 6 amps and it hit a junction? Well, it has to split up and those two have to add up to 6. So 3 and 3 is clearly 6. And they should be the same current because they have the exact same resistance they're going through. So now we know that I2 and I3 are both 3 amps. Now remember, if we had just divided that in half, that voltage, to 12 volts, we wouldn't have gotten 3 amps. It wouldn't have made any sense. Now let's come down to I4 and I5. Okay? On I4, we have 12 volts and 6 ohms. That would give me 2 amps. But on I5, we have 12 volts and 3 ohms. That gives me 4 amps. But that still makes sense because 4 plus 2 is 6. It also makes sense because 2 amps goes through the 6 ohm and 4 amps goes through the 3 ohm. In other words, a higher current goes through the lower resistance. So I4 is 2 amps and I5 is 4 amps. And look at that, we've got everything else we've asked for. We found the voltage drop everywhere and the currents everywhere and the REQ of the circuit. Okay? Simply by following those steps. Reducing little bits of the circuit till we got to the simple circuit, found REQ, then we found current, brought current back, found voltage drops, and really what we did is we brought their voltage drops back to find all of our currents. Notice there's sort of an alternating fashion that's going on here. Going forward, I reduced a parallel and then I switched and reduced a series. Coming backwards, I found current, and then found voltage drop, and then found current. Notice it's kind of alternating, and sometimes if you're doing the method the best way, things will alternate like that. Alright, I know, tough to initially follow, right? Well, let's look at another example. Okay, so here we have a 60 volt source. Let's follow our current, I1. Comes out, hits a 2 ohm resistor. But then it immediately hits a junction, splitting into I3 and I2. Now, I2 goes down to 10, but I3 goes through 6, 1, and 3 before joining back up again and becoming I1 again through the 8 ohm resistor. Now, you got to be really careful here. Because of that first junction, okay, the 10 ohm resistor is not in series with anybody because it gets its own current, I2. But I3 goes through 6, 1, and 3, so they must be in series with each other. They get the same current. Now I1 goes through 2 and 8, so 2 and 8 are technically in series, but they don't really look like it, even though they are. So I'm probably not going to want to mess with 2 and 8 right now. So again, I got to decide, what could I reduce really easily? Well, and also, I'm sorry, be careful. 10 and 1 are not in parallel with each other. 10 and 1 are not in parallel with each other, even though they look like it. And that's because the 6 is in the way of them being in parallel. But because I3 goes through the 6, 1, and 3, they must be in series. So I'm going to reduce just them. So in other words, I'm going to keep the 2 ohm, I'm going to keep the 10 ohm, and I'm going to keep the 8 ohm alone. And then I'm going to squeeze together 6, 1, and 3. And since it's series, I just have to add them up, and that gives me 10 ohms. Okay? That was pretty easy to start. Now, remember that alternating idea? I just reduced a series. So what I should look for is to find a set of resistors in parallel. Well, again, the easiest thing to find a parallel is look for a junction and look what immediately follows it. And right after that junction are those two 10s. So they must be in parallel. So if we do a mini reduction, 1 over R, would be 1 over 10 plus 1 over 10, which is 2/10, or 1/5. So I'm going to redraw the circuit. And I'm only squishing together those 2/10. So the 2 ohm still stays. The 2/10 are now squished together to make a 5 ohm resistor, which I found from there. And my 8 ohm is still there. Okay? Now remember, I just reduced a parallel, so I should look for a series to reduce. Well, it's pretty obvious I've got a series now, because that 2, 5, and 8 are all on one thing together. So now I can get my simple circuit, and when I add those together, I get 15 ohms. So 15 ohms must be the REQ of the circuit. And again, notice how we did that. First, I reduced a series, 6, 1, and 3. That gave me 10. Then I switched over and reduced a parallel, the 2/10. That gave me a 5. And then I switched over to a series, and that gave me a 15 ohm REQ. That's the moving down method. Notice how it alternated. Now, let's go backwards. Well, I've got voltage and resistance. I can find current. 60 volts, and again, we're just looking at Ohm's law, V equals IR. 60 volts and 15 ohms must mean 4 amps of current. 60 divided by 15. Now, notice I just found current. So I bring that back, and to alternate, since I just found current, I want to look for voltage drop. Well, I run the 4 amps around the circuit. 4 amps times 2 ohms is 8 volts. 4 amps times 5 ohms is 20 volts. And 4 amps times 8 ohms is 32 volts. And now here's my quick check. 8, 20, and 32? That adds up to 60. I must be in good shape, right? All right, let's come back. Let's bring my 4 amps back first. Now, things I can bring back. Well, the 2 ohm resistor still exists, and we already know it drops 8 volts. The 8 ohm resistor still exists, and we already know it drops 32 volts. Now, we haven't brought back that 20 volts. We need to bring it back, right? Well, the 5 ohm resistor came from the 2/10. Now, since the 5 ohm dropped 20 volts and it's a parallel group, they each drop 20 volts. Okay? So now I brought everything back, right? In that previous circuit, I found voltage. So on this new circuit, I probably need to find current. I need to alternate. We already know 4 amps comes out, but after the junction, I have 20 volts and 10 ohms. That must mean 2 amps, 20 divided by 10. The other one, also 20 divided by 10, 2 amps. Now, my quick check, 2 plus 2 equals 4. Again, I must be doing okay. Now, be careful. You might say, well, the voltages no longer add up to 60. Well, actually they do, because remember, those two 10 ohms are sharing that 20 volts. So you don't add them together, they're considered one 20 volt source. So I'm still conserving energy, I'm still doing my voltages right. All right, let's go back to the main circuit with everything we know. I know this is 4 amps, I know this is 2 amps, and this is 2 amps. Hey, I know all my currents. I1 is 4 amps, I2 is 2 amps, I3 is 2 amps. That's good. Voltage drops. Well, the 2 ohm I still know drops 8 volts. The 10 ohm I already found out drops 20 volts, so that's still there. And the 8 ohm drops 32 volts. Okay, so I've got some of my answers there. Okay, the voltage on the 2 ohm is 8 volts. The voltage on that 10 ohm is 20 volts. And the voltage on that 8 ohm is 32 volts. Now, I have not brought back this 20 volts. I need to somehow bring it back, but I can't just put it somewhere because there's no one resistor to go at. But that 10 ohm represents a 6, 1, and a 3 in series. Now, on this previous circuit, I found current, so I'm probably going to look for voltage drops, and that's what I need to do. If I follow I3, it has 2 amps. 2 amps hits 6 ohms, must drop 12 volts. Comes around, 2 amps hits 1 ohm, must drop 2 volts. Comes around to the end, 2 amps hits 3 ohms and must drop 6 volts. Now look at this. 12 volts plus 2 volts plus 6 volts gives me 20 volts. I brought back my 20 volts. Okay? Everything seems to be working out. And now I know all the rest of the voltage drops. 6 ohm dropped 12 volts, 1 ohm dropped 2 volts, 3 ohm dropped 6 volts. So now I've got all those answers right there. Okay? One last question here was, what's the total power of the circuit? Well, if I want a total, I always come down to the simple circuit. Any totals are found at the simple circuit. So I can do P equals IV for the whole circuit. I is 4, V is 60 for the whole circuit. So the total power the circuit uses is 240 watts. And that's basically how the method works there. Let's see how this would look on a simulation. Let's see if we're doing this right. Okay, so here is my simulation of that circuit we just did. 60 volt source, 2 ohm, 10 ohm, 8 ohm, 6 ohm, 1 ohm, 3 ohm. Now remember, we found there was a 4 amp current coming out of the voltage source, and when it split into 2 and 2. So the currents look right. Voltage drop. Well, this 8 ohm one, oh look, 32 volts, just like we had calculated before. The 2 ohm, that dropped 8 volts, that matches our calculation. The 10 ohm, I believe we had that dropping 20 volts, yep, that works out. The 6 ohm, I believe we had dropped 12 volts, yep, that's working. The 1 ohm should have dropped 2 volts, 2 volts. And the 3 ohm should have dropped 6 volts. And it does, 6 volts. So, looks like everything worked out the way it should have worked out. So, that's basically how to reduce a complex circuit. And again, it does require some practice. Again, the steps in solving this the best way. First of all, find something that's easy to reduce right away, either a series or a parallel. Okay? And whichever one it is, and something as you saw in the previous example, we could do 2 parallels at once. Okay? What you never want to do is in one motion do a series and a parallel. That will mess you up. So pick one or the other. Either do a series or do a parallel. Again, you could do a couple of series all at once if it fits, but you also notice it's always best to work far away from the voltage source and work your way in towards the voltage source. So whatever reduction you do first, if you do series, the next reduction you want to look for is parallel, and then the next one will be series, and then the next one will be parallel. And keep alternating until you get down to that simple circuit. Once you're at the simple circuit and you've got REQ, find your current. Bring that current back, run around and find voltage drops. Bring everything back and find currents. Bring everything back and find voltage drops. Alternate. And if you follow this through, you should be able to solve just about any complex circuit there is. All right, well, good luck on that one. I know it's going to be tough, but with enough practice, I think you'll really get it really quickly. We'll see you next time.